In 1907, Albert Einstein proposed a thought experiment to interrogate the precise nature of gravity. He asked us to imagine an observer inside a sealed box, floating in deep space, being uniformly accelerated upwards by a constant external force. Inside this accelerating box, the observer holds out a single test sphere and drops it. The floor accelerates upward to meet the sphere at a constant rate. Now, place an identical sealed box at rest on the surface of a planet with a true gravitational field. The observer drops the exact same test sphere. In both boxes, the single sphere falls to the floor in exactly the same way. From the perspective of the observer trapped inside, the two environments look identical. This is the Einstein equivalence principle, the assertion that a gravitational field and uniform acceleration are locally identical. On the strength of this indistinguishability, Einstein identified gravity as the geometric curvature of continuous spacetime. For a century, physics has built its entire geometric model of the universe on the assumption that the conditions of this single scenario hold true universally. The quantum geometry dynamics framework, detailed in paper P45, subjects this foundational premise to a strict axiomatic review. The analysis asks whether this indistinguishability was ever proven mathematically for all physical cases, or if it was simply read off a single convenient case. Einstein's entire argument relies on observing the behavior of a single test mass. QGD breaks the indistinguishability claim by introducing a second mass into the protocol. If true gravity and simulated gravity are distinguishable in practice, the geometric foundation of spacetime fails, requiring a new mechanical explanation for how objects move. To see where the thought experiment fails, we have to look at the exact mechanics of acceleration under the QGD framework. This is the formula for true gravitational acceleration. It follows the weak equivalence principle. The gravitational interaction is directly proportional to the mass of the object being accelerated. Because that mass term cancels out completely, gravitational acceleration is entirely independent of mass. Now, look at the formula for propulsive acceleration, used for rockets or thrust-accelerated rooms. In the propulsive equation, the mass of the accelerated object sits in the denominator. Unlike gravity, propulsive acceleration remains inversely proportional to the mass of the object. QTD derives these as two structurally distinct mechanisms governed by different functional laws. Einstein's equations coincide numerically for exactly one chosen mass at one instant, which is precisely how his thought experiment is constructed. Indistinguishability is a mathematical coincidence of the single mass setup, not a universal law of nature. We can verify this result by returning to the elevator and running a two-mass discriminator protocol. In the green room, resting in a real gravitational field, the observer holds two spheres of vastly different masses. Both spheres are released simultaneously. Because mass cancels in gravity, both spheres hit the floor at exactly the same time. Now we move to the red room, accelerated by external thrust in deep space. The observer drops the same two spheres as the room accelerates upward. Because propulsive acceleration retains its mass dependence, the two objects react differently. The observer records a mass-dependent drift relative to the floor. The illusion of gravity breaks. In the red room, releasing the heavy mass abruptly reduces the total weight on the floor. Since the upward thrust remains completely constant while the payload has dropped, the room experiences a discontinuous jump in acceleration. Gravity acts continuously on every constituent, whether it is released or not, so the green room produces no such jump. This felt force asymmetry is available to the observer directly. When subjected to a two-mass test, Einstein's equivalence principle fails. True gravity and simulated gravity are completely distinguishable in practice. If the equivalence principle is flawed, we have to explain why general relativity works. Its observational successes, like time dilation and the deflection of starlight, are genuine and precise. Any successor theory must account for these elliptical paths without the geometric framework Einstein used to predict them. QGD recovers these precise numerical results without relying on a curved spacetime metric. It derives the weak equivalence principle independently, preserving the universality of free fall that we observe in the lab. Within this framework, gravity operates via discrete, instantaneous momentum vectors rather than geometric slopes. QGD does not discard the confirmed predictions of relativity. It replaces their underlying mechanical cause. The math of general relativity works because its geodesic formalism tracks the same instantaneous gravitational vectors that QGD computes directly. Einstein's equations get the right answers by using curvature as a language to describe what are actually discrete momentum transfers. This is the geodesic approximation. General relativity correctly tracks the results of gravity while incorrectly encoding them as spacetime curvature. The math works perfectly as an effective description, but spacetime itself does not physically bend. Under this paradigm, the status of Einstein's equivalence principle changes. It is a brilliant and highly effective single-mass approximation, but not an exact local law of physics. Gravity and acceleration are indistinguishable in principle for a single mass, but distinguishable in practice the moment we add a second mass to the room. Physics can maintain dependable accuracy of relativity while anchoring its foundation in a discrete, logical reality.